don't mind saying, I don't know, who don't mind saying, oh, that's interesting. I need to learn more about that, because that's exactly what we are doing today. We are learning about the electric stack via Paddy McCormack's not boring essay, The Electric Slide. This is part 2, power electronics. A quick reminder, a quick summary for those of you who are new to this. The electric stack: lithium-ion batteries, magnets and electric motors, power electronics, and embedded compute. Together, those 4 things make the electric motor possible. And the electric motor is in everything. If it can go electric, as we learned last week, it will go electric. Electric cars, your Tesla, your toothbrush, your washing machine, your drone, your dishwasher, your humanoids, your, I don't know, if it's made of, if it's electric, it involves electric stack. And China has a complete domination of the electric stack. We'll read out some of the data, but those 4 parts, it's all Chinese. America is playing catch up. And the other important thing you need to know is that the cost of each of those parts of the electric stack has dropped 99% in the past 2 decades.
99%.
99%.
Let's let that sit just for a second, because it's pretty powerful.
Yeah, technology is cheaper, more accessible, more available to everybody. I'm sure that's the same for all technology. It gets the value to make it decreases. It becomes more widely used, more widely available. It bleeds through into other technologies, and it's just this flywheel of progress. And the electric stack is in the midst of an incredible evolution. So yeah, the electric stack, power electronics, Jeremy. When I say to you power electronics, now you know the answer to that. What are power electronics?
Packy has some really cool sentences in here, especially for guys like myself who aren't an engineer. I've never, soldered any kind of, old transistor.
You've never soldered. I can
maybe I've
imagine
soldered.
you in your shed.
Maybe I've soldered before, but no, just like, it's really interesting to think about the harnessing of electricity into motion. Harnessing of electricity into motion is really what we're talking about in this whole stack, and power electronics, as I understand them. And guess what, guys? I am uncomfortably learning in public today. You are going to definitely see me wincing and maybe steam come out of my ears, but this is the right way to do it, because it helps us get there. But power electronics basically give us the ability to do that harnessing more efficiently and targeted for specific outcomes. So that's what I would say, just from a high level, on power electronics.
Yep.
What up? Muller's in the chat. Muller's in the chat.
Well, Muller, what is power electronics? I'll quote from the essay. So, if batteries are the heart of the electric stack and magnets are its muscles, power electronics are its nervous system. They shape raw electricity into exactly the right form, in exactly the right direction, at exactly the right time, to make motors spin, batteries charge, LEDs glow, and grids hum. Power electronics control how much current to send and in which waveform. And since 1990, as I've already alluded to, they have fallen in cost from $400 per kilowatt to $2. That's a 99.5% reduction, actually. So yeah, power electronics. Anyone else in the chat?
Yeah, Muller's jumping in. So yeah, Muller stirred the pot in the social realms for thinking on paper as of late. That's been a fun discussion. Let's stay on track with power electronics, though.
So we've got 2. It's a story again. Once again, it's a story of Japan. It's a story of America. It's a story of a few very, very, very smart people, and it's a story eventually of China taking that knowledge, taking that know-how, taking that acumen, taking those companies and creating their own power electronic stack. So this is where it gets complicated, Jeremy. This is where a lot of my learning came in researching this. We have BJTs, IGBTs, we have MOSFETs,
That's a great one. I like that one a lot.
the MOSFETs. So we're going to try to understand how bipolar junction transistors, insulated gate bipolar transistors, and metal oxide semiconductor field of effect, which is something I never thought I'd say live on television, but I just did, and how they kind of fit together to eventually bring us to the Tesla Model 3. And we focus on the Tesla Model 3 because it is the perfect example of the electric stack, those 4 layers of the electric stack working together in union to create something that most of the Western world is familiar with, the Tesla S3. And to quote again from the essay, Tesla didn't make the Model 3 cheap by using cheaper parts. They made it cheaper by redesigning the entire system around better parts.
Actually, using more expensive pieces.
Yeah.
Initially, which turned into something pretty groundbreaking. Not just on a number of fronts. The engine too, taking an ABB engine ABB motor, and kind of compiling that with the SiC MOSFET, right, or the SiC MOSFET, right, to make it even better. So combinations of these technologies that have happened over time, piecing these things together, that's led to some of these giant reductions in cost, driving innovation, and some really cool stuff. What do you want to pull from some of these? I don't know that we have the prowess to dive in to the inner workings of BJTs and MOSFETs and IGBTs. But what did you take away from this section as most important to carry into this Tesla case study?
My very high level understanding of that, there was kind of an order for these BJTs, bipolar junction transistors, were the workhorse of early electronics, but they low voltage, low current, slow, and because of, was it General Electric?
General Electric.
Again, after the 1973 oil crisis, they were looking for a way to research more, looking at ways to save energy, basically, in their motors, weren't they, to make them more efficient. And they took the BJTs and improved on them to make IGBTs, insulated gate polar transistors. There was a man called Jayant Belinga who worked for General Electric, essentially came up with, quote, Belinga realized that the key is to decouple the input from the output. Okay, so it makes them more efficient. You get the IGBT, and then again, that's built on, and you get these MOSFETs, which combine the two technologies to speed up.
But like General Motors back in the last example, sold off the what was their division that they sold off to China? Was it related to magnets or batteries? I think one of the two sold that business to China, or not to China, the country, but to entities in China that ran with it. GE sold the semiconductor business in 1988. After Belinga does all this great stuff, he ends up landing, I think, at North Carolina State University, right? Where
not far from you.
Not far from me, the Wolf Pack, right? So it's interesting. I think there's again this idea of and Packy hits on it at the takeaways at the very end, that what seems to make sense in the short term rarely looks good in the long term, which is GE selling that business. What would that have done to prepare or to give the U.S. the advantage, or give U.S. the advantage in some of this part of the stack, right? So what did all this?
I just want to go back on that because I found the part I wanted to quote. So rather than trying to understand or tell the world what IGBTs are. You should go on the essay, read it. I want to read how important they are. So the quote, the IGBT allowed fast electronic switching of large amounts of current for the very first time. By 1985, everybody went bananas with this. Now they had fast devices. They could start running with it. It just took off. Even though we don't think about IGBTs very often, it is hard to overstate their impact. Without IGBTs, you can't effectively convert battery DC to motor AC. Without IGBTs, you can't do regenerative braking. Without IGBTs, motors are stuck at fixed speeds. No IGBT, no electric stack. No electric stack, no modern world. IGBTs, and this was amazing, have saved more energy than any invention in history. When Baliga won the Global Energy Prize in 2015, the committee wrote, in the last 25 years, IGBTs saved over 73,000 terawatt hours, I think, of energy, over 1.48 trillion gas gallons, and decreased CO2 emissions by 49.5 million metric tons. The customer's savings exceeded $23.7 trillion.
So what was our alpha product that this all shook out? What was the alpha product?
Well, just before I tell you what the alpha product is, what is an alpha product as regards the electric stack?
Well, as we talked through a couple times, there's one product that generates this inflection point, right? That changes the game, that puts something out there that accelerates innovation, that drives savings, that brings other pieces and parts together. So the example of the alpha product in the last one with I think it was related to magnets, correct? Was the hard
batteries.
Drive.
Oh yeah, and batteries was the handycam. Yeah, magnets was the 3.5-inch hard drive. Yes, correct.
Right. So it's interesting to walk through these alpha products. So ton of energy savings, right?
Yeah, some of those stats are, I don't know how they work those out, but even if they're overestimated, they're incredible. The alpha product for power electronics was a variable frequency driver, a VFD. A variable frequency driver is a device that controls the speed and torque of an electric motor by changing the frequency of the electricity sent to it. A VFD takes in power from the grid, AC, or a battery, DC, and converts it.
So think about the idea that we talked about before with electricity into motion and power electronics, harnessing that very efficiently. This is the prime example of that. And if you think about it, before VFDs, if you wanted to try to run a motor at half speed, you still have to pay for the cost of running it at full speed. It's the analogy that they used was like driving with one foot on the gas and one foot on the brake. And before VFDs, you couldn't really do that. Now translate that forward to today, from a data center perspective, when VFDs were introduced into data centers, it created tremendous efficiency where, just to give you a stat, power usage effectiveness, it's the ratio between the IT power load and the systems that support the IT power load. Right. Back before VFDs, it was about 2.0 was the ratio. And then once VFDs were introduced into data centers, it dropped to 1.25. So think about that over megawatts of power and kilowatt hours and all of that stuff. I mean, drives tremendous efficiencies. But even in between that, there were so many different systems that were affected, and energy efficiency translated through to consumer products and all of that stuff. But I wanted to touch on data centers because everyone's talking about those. PS Thinking on Paper was talking about data centers in space nearly 2 years ago when other outlets were not even mentioning that. So, just a nod.
It took Elon Musk to bring data centers in space to the mainstream narrative, but Thinking on Paper was there.
Wait, are you saying Musk has more pull on the press than we do?
Well, for the time being. So with VFDs, have I got that correct? VFDs.
Variable frequency drives, yeah.
Are they responsible for taking the fun out of cars. And I like the gear shift. I like clutch, gear, accelerate. I like the sound. I like the manual sound and function of that engine. It's essentially, is that what they've done? Made it, taken that part of the driving experience out?
Taking the fun out of driving, man. But hey,
I know.
there actually are companies right now that are retrofitting really cool old cars like VW buses and old Broncos and that sort of thing with the electric stack essentially. It only costs about $200,000 for them. So if you got that sitting around, it's probably all good.
Were we talking about this the other day, like the future of spaceships? When we're all traversing space and going on space holidays, all of the ships will be outfitted or pimped with amazing sound effects, so they sound like rocket ships rather than electric vehicles. Talking of the nostalgia and romance of old driving, I think that leads to the romance and nostalgia maybe for our youth and some of the Toshiba, Mitsubishi, Panasonic, these old, not old, but these Japanese companies from the 80s and the 90s, which were responsible for all of the hi-fis and games consoles and gadgets that we all wanted when we were growing up in the 80s and 90s, and how they were a big part of all of this. In the mid 80s, quote, two Japanese conglomerates, Toshiba and Mitsubishi, refined the IGBT manufacturing process, while two others, Yasukawa and Fuji Electric, rapidly pod I can't say that word. Productized them. The Japanese were
That's a
ready.
Productized. That's a weird word.
That is a weird word.
Well, this
What I
is
liked
this.
about it.
Yeah,
Sorry, you go. Well, you go on.
I was just going to say this is a nod to before taking something that's already existing and making it better. There was a Japanese phrase for it. I can't recall it, but we referenced it in the last one. It's like taking a piece of something that's already developed and refining it and making it better instead of inventing something entirely new.
Yeah, that was the yeah, forgotten word.
There was a
Well,
cool little phrase for it. Anyway, listen to the last episode, guys, and you can find it.
and they were what they were doing. So Mitsubishi, they were leveraging their experience in the process, but they were vertically integrated, weren't they? So they could improve, and then that improvement would go straight to another part. So Mitsubishi Electric made motor drives and industrial equipment. No. Where's the bit? Well, vertical integration rather than everything's made in one place, and so the improvements bleed through into other parts of the process very quickly, and takes what would take months in a globalized company can take days or hours even within these integrated companies.
Shall we bounce back to Belinga for a second?
Yeah.
So Belinga leaves General Electric, lands at North Carolina State, mainly because, or allegedly mainly because, as it's referenced in the essay, North Carolina State has access to something called gallium arsenide, which is an ingredient to make a more efficient MOSFET, right? So is that right? No. I'm sorry. Let me reverse that. So gallium arsenide, what was put together is what was used in MOSFETs, right? So NC State has access to something or had access to something called silicon carbide, which is the SiC in the SiC MOSFET. So that's what Belinga was working on. It's super hard to make, you know, versus the gallium, but it actually works really better, quite a bit better. Um, so that's what kind of drove this efficiency in the MOSFET. So now we got SiC MOSFET that's basically used in bullet trains in Japan. It makes the bullet trains kind of roll quickly in Japan, and now we're into Model 3, right? Model 3 case study.
Sorry, I was just looking at silicon carbide and how it's made.
Yeah, 2,000 degrees Celsius in weeks to make a single wafer.
well, the Acheson process, invented in
Yep.
1893. But
It's
okay,
almost
so
like
it's very, very time consuming.
alchemistic. Yeah.
The alchemy of the electric stack.
Yeah, right? So, yeah, so do we want to let's land on why Packy chose the Tesla Model 3 um to run through this. So, Elon throws the gauntlet out, says, "Hey, I'm going to make a an electric vehicle for $35,000 and it's going to have 215 miles of range." Bam. Why does this work as the case study?
It's a bit like Steve Jobs, isn't it? Where Elon Musk says, "I want this, this, and this. Now go make it happen." And
Right.
which is that's what he did, isn't it? He didn't really have that product at that price, but he wanted it, so he said that, and the team went and did it. The Model 3 is the example because it combines all layers of the electric stack in a way that um, the Model 3 is one of the best examples of what can happen when you design a vertically integrated product using cutting edge components from each layer of the stack. Can I share my screen? Because the picture, as Packy says himself, the picture
Oh, between the
much,
IGBT and the SiC MOSFET? Yeah. Can you share your
yeah,
screen? That's a good question.
I can. There you go. The
Oh, yeah.
2012 Model S silicon IGBT drive inverter versus the 2017 Model 3 SiC MOSFET drive inverter. Chalk and cheese, as they say.
Chalk and cheese.
That one looks like the inside of a washing machine, and this one looks like a high-tech chip
Yeah, and that's what
silicon
a
wafer
5 year
plate.
5 year difference in technology there, right?
Yeah, it's pretty impressive, isn't it? Where are we going to be
So
in another 5 years?
so we combine this SiC MOSFET, which basically delivers faster switching, right? With this motor that I think was originally created by ABB, the IPM SYN RM motor. So again, we're taking old pieces, we're combining them in new ways. Isn't that creativity, Mark? Careful rearrangement, curated rearrangement of found elements. That's what we're doing. We're picking up these pieces, we're tweaking them a little bit, and it's leading to massive innovation. And this massive innovation drives demand for new products. Costs are coming down. Now,
Do
how
you
can we?
think scientific engineering, creativity, and curiosity like this is mind bending what's going on for me to watch this progression in such a short period of time? Is that the same? Are the same brain juices and chemicals firing for when you're writing a song or writing a poem as when you're being creative in a scientific or engineering way like this?
Man, I think it. Yeah, it's whether the inputs technical or the inputs emotional, and like what are the outputs of that. And so, are you asking? Is the question you're asking, is it the same juices flowing when it's a scientific output versus a creative output?
Yeah, like if you did some, what are those the MFI scan, the brain scans
Oh,
on,
fMRIs? Yeah.
if you did those brain scans on um what's his first name, if you did those same brain scans on Beliga, and you did those as you did on Stevie Wonder, would they show the same thing?
It's very interesting. We might soon be able to observe that with brain machine interfaces. God, the world's getting scary, Mark. What are we? Can we go back to driving clunky cars? And
Is all creativity the same, I guess, is my question.
I think, well, let's unpack creativity, right? I know we're taking a hard right turn here a little bit, but we always talk about inputs and outputs, right? And rearranging those inputs and outputs in a unique way, putting a new stamp on things. creativity requires curiosity. So are these people curious? Yeah, Belinga, there was a quote here. I think that as he was leaving General Electric, let me find it. That was related to curiosity or him chasing his curiosity. Let me see if I can find it. Um, anyway, he talks about curiosity. A lot of the people, oh, I had quote when he left GE to go to NC State. I had an intellectual curiosity. What can I do if I change the material? So this is when he was starting to think, the gallium arsenide versus the silicon carbide. What if I change the material, right? So there's a curiosity, this what if idea, but there's also this like I don't give a shit if I fail. Like if I mess up or something stupid comes out of it, I think there's a willingness to explore without expectation. And then you had sprinkle in a little bit of a drive to succeed. This is the ingredients of creativity. You have to think that the process is similar across different disciplines. It's just
So like Kraftwerk were doing a similar thing. It's like what happens if I run this through this, or what happens if I press this button and turn this knob? What if I change the ingredients of this melody? The same idea of what if I change the ingredients of this transistor?
I think it's a curiosity. And like we always reference the Tom Waits quote, he believes we're in a deficit of wonder. I think you have to have some aspect of wonder and awe and not just have the answer, but being willing to wander through some shit to find the answer and enjoy it.
I'm not so sure we're in a dearth of it anymore. I think we're barbelled for it, where a
Mm.
small amount of people own and wield most of the awe and wonder.
Oh man.
How about that?
Jeez, Mark. We all right, let's swing the pendulum back to maybe not optimism, but somewhere in the middle. Just a
Well, to be
neutral.
honest, I did that aside so I didn't have to get into the
Embedded compute.
the IPM SYNRM, which was developed the IPM series. Some of the Tesla terminology is far beyond me.
Well, that's a motor that was not developed by Tesla. It was used by Tesla and combined with the SiC MOSFET to make that Model 3 more efficient, among other things, right? So let's run down the journey a little bit and continue. So I thought this was interesting when he starts talking about China and Tesla. So China actually allowed Tesla to build a massive factory without a partner, which was the first of its time. It usually required a domestic partner, right, for some of that stuff. Um, and there was this little piece of it that talks about Tesla being the catfish to China EVs sardines, right? So the analogy of did you pick up that? It
Yeah.
took me a second to get it, but like sardines. If you pull them out of the ocean and you chuck them in, and they die on the way in. The ones that stay alive actually taste better. So what they started doing was putting catfish in with the sardines, keep the sardines alive. The sardines taste better. So the reference here was Tesla was the catfish that did a couple of things that made EVs more attractive to Chinese consumers, right? There's that piece. But what they also did was they helped develop or they helped make better the vendors that supported the building of EVs in China. And then you have companies like BYD who come in, and we talk about vertical integration is like all up and down this essay, and Packy has written essays on just vertical integration alone. So BYD starts to go, okay, how far upstream can we go to continue to own this model? So the little pieces and parts that make SiC MOSFETs, they're looking to own some of that stuff. So they're building their capability. But what's interesting, Packy says that US actually has a slight lead in SiC MOSFET production.
Well, that's the interesting part of the whole power electronics part of the stack, isn't it? I mean, I I'm from England, and our position on the global stage has been well advertised of late. So I have no qualms in belittling America's participation in this race. But in this particular stack, as he says, power electronics remains a much closer race than batteries or motors and magnets. But that's possibly because China only entered the race about 20 years ago, whereas in the others they've been in the race for longer. So we'll see what happens in the next 20 years. Quote, the country has understood the importance of semiconductors since the 1950s, but early efforts were primitive and were disrupted by the Cultural Revolution of 1965 to 1975. But then in 1978, under Deng Xiaoping, China redoubled its chip efforts. And then we get the story of how the early iterations were pretty terrible, really. There was one American researcher visiting a Shanghai factory in the mid 1980s, found it was producing chips that were 10 to 15 years out of date, with yields as low as 20 to 40%. So rubbish compared to the American counterparts. But as China tends to do, they learn very quickly and they evolve very quickly. This was mind blowing for me. So we get some more about the Chinese technology development plan. So these 5-year plans that the Communist Party introduced. 2008, China opened its first high-speed rail. So in less than 20 years, they've completely covered their country with high-speed rail. And at the same time, in the UK, we've failed to build one high-speed rail link.
Ideas into action is kind of the thing that they've gotten really good at, scaling the idea and implementing.
Well, I mentioned the high-speed rail as well because those IGBTs were all over the high-speed trains. So they're building lots of trains, and you talked about this integration. So by building lots of trains helps you to build electric cars and drones and toothbrushes and humanoids, doesn't it?
Yeah, you do it for one thing and you apply it across multiple industries. Yeah, no, that's what they've done for quite a long time. Actually, quite impressive, man. The narrative for China from a U.S. perspective is this scare, like we have to beat them, and they're the enemy, and this and that. Just in the U.S. domestic press, but when you kind of take a look at what they're actually doing from a capability perspective, it's pretty impressive.
Is this a cultural thing? So in America and Europe to a lesser extent, we're taught from a very, very young age about the importance of I, and everything is a competition for me, and I have to evolve to this. Whereas in China, and I'm obviously no expert on Chinese culture, but there is a much more collective unity for China, for the nation, for the country, where everything is done for the greater good rather than the individual. Do you think that plays a role in this?
Possibly. That's the then we get into that, then we get into that kind of socialism, democracy discussion, and yeah, which we don't have time for today. So let's move to
Check out our Instagram account, though. There's lots of going on there on
Holy
democracy.
smokes, right? All right, so let's go to speak and spells. We're kids of the '80s and '90s, man. Did you have a speak and spell?
Yes, I did. So I was very young. I don't. It's not. I remember having it, but I don't really remember using it or playing with it. It's just before my
Are we
time.
5 years apart? How old are you?
4, I think. Yeah,
Okay.
I was 79. I was born.
Oh, 76. Okay. Yeah, I had speak and spell, speak and math, speak and read. Like I remember having those, and they have the little handle on them, and like very visceral memory for me with that. But as we go into embedded compute, I thought this was really interesting. Right now in the news, everyone's talking about GPUs and that sort of thing. But this section brings up a couple of other pieces that we don't tend to think about a lot in electronics, um, or those some of those discussions is the microcontroller and the digital signal processor, right? So, but without these MCUs, these microcontrollers, you know, a lot of what we see in electronics and in the IT world can't really happen. Um, so maybe let's talk through the MCU piece just from a super high level. So
Oh,
this
have you gone into embedded compute?
yes, yes.
Okay. Well, I'm flying blind here.
Yeah, we're just we gotta kind of land the plane here in a minute.
You gotta-
Yeah, we gotta get the DSP to solve the problem and feed it to the MCU so we could land the plane, so we could land the drone. Um, no, so these really quickly, just this was pretty interesting that MCUs operate as this hub, but when the tasks become really complex and difficult, it kind of outsources some of these calculations to the DSP. The DSP sends it back to the MCU, and kind of creates signal from noise a little bit. Um, so the MCU's alpha product was the calculator. We talked about the speak and spell, which included a speech synthesizer, which was pretty cool. 500,000 units, and guess what? Finds its way into one of the most iconic movies of all time in 1982. E.T. attempts to phone home through the speak and spell. Um, Stay with me here because I'm just gonna kind of stay on my track. Acorn Risk Machine I thought was really interesting. So, 1983 was kind of a big year for the electric stack, right? You had, if you remember, you had Sagawa and Croat kind of battling, wielding their own version of neomagnets at each other. Well, at the same time, um, Acorn Risk Machine was putting this new technology, this new capability to play, and companies like Intel were like, you know what, this little design you're building is kind of niche. I don't really think it's going to do really well. The performance kind of sucks. Good luck. So, a couple steps later, Apple releases a failed product called the Newton Message Pad, which looks like this early version of what might have become the iPad later on. And these ARM chips, right? And I think it's a chip, ARM chips made that thing possible, but the product failed. But they're like, you know what, these chips could be really cool. And now kind of mobile comes out. It's like, well, how do we power these little small computers we want to hold in our pocket? Intel's like, this ARM shit is dumb because it's not powerful. Our stuff's way better. But guess what? ARM becomes kind of this standard for electronics, for microelectronics, for phones and that sort of thing. They did it a little differently though, didn't they, Mark? Instead
Did
of
they do tell?
so so they ended up kind of making this a licensing play instead of making their own chips. A lot of other they licensed their technology, the ability, here's the ingredients, you guys go make your own chips, right? And then you have RASC-V. The wrist, I don't know how they say that, but it's RASC-V, which basically is like this Linux to Unix thing, right? It's this open source version of this tech that's already out there. We're light speeding here, Mark. We're on the
Just
we're on
go
the
with it.
bullet train powered by IGBTs, firing through the rest of this stuff. But what makes that last thing so interesting that I said, it provides this it provided the opportunity for semiconductor independence for China, even though actually as of today or yesterday, I think Nvidia is now allowed to sell their chips over that way. So
It'll be interesting what happens with that Nvidia announcement, and because there'll be some people in China who won't want that, and maybe that's why the Trump administration has turned their decision to allow Nvidia to sell their chips to China, because it might slow down their own advancements in the manufacture and skill set that they have. Um, let's land this plane with the lessons from the history of the electric stack.
there you
So,
go.
If you've made it this far, congratulations. You now know more than about the electric stack than 99% of the world. So what have we learned? So in the essay, he outlines 8 key lessons. So let's just run through those. I'll read them out and then we'll see. Well, have you got it up there as well?
Yeah, you want me to
Okay.
read it?
I'll do lesson number. Take it in turn. Lesson number 1: the fact that the world has reduced the cost of the components that turn electricity into motion and all sorts of other useful work by 99% in 3.5 decades is one of the defining miracles of our time. Do you agree? I think I agree with that.
Sounds about right. Sounds about right.
So, what's lesson number 2, Jeremy?
So this talks about demand driving innovation, right? So the reason for that demand driving innovation is because things get cheaper, right? We're 99% cost reduction. The pieces and parts are cheaper, and we're now able to kind of drive new innovation with that. And, the Handycam was kind of that alpha product. We talked about VFDs being that alpha product that generated a ton of demand for uses very similar to that alpha product, right? So I would agree with that one as well.
Okay, lesson number 3. There's typically a decade or 2 gap between scientific breakthrough and scale. Science isn't enough for the research to lead to impact. Manufacturing it into products is necessary. I'm sure that decade or 2 that gap will decrease, but yes, needs must. I don't think that's new, but I'll take that lesson.
Yep. Number 4, I don't know how I feel about this one. He talks about talent can come from anywhere.
Talent isn't destiny, and that talent can come from anywhere throughout our story.
So I think, I mean,
yeah, I mean, I guess what he could mean there is that you don't need to go to Harvard to be the source of talent necessarily. Talent can come from anywhere. Yeah, you can be what you want. It's the American dream. Lesson number 5: American innovation.
Was that your American accent attempted? Can you do an American accent?
It's funny because my niece is a wannabe film director, and so sometimes we do these. Basically, whenever I have to act, I put on a stupid American accent. Yeah, and it sounds like that.
Okay, can you read the next one with an American accent?
Okay, lesson number 5: American innovation in the electric stack consistently came through partnerships with other countries.
Oh my God, that's outstanding. That's outstanding. Um,
I forgot what I was reading.
no. So American
Do you have to
innovation.
read the next one in English, in an English accent? You have to do
American
your.
innovation was through partnerships, right? So instead of kind of doing it on their own, they kind of partnered with other countries, companies to kind of make. What's an example of that one, Mark?
Rather than what's an example of that, I think that America should read that lesson and take it to heart and stop trying to do everything on their own in 2025 and beyond. Maybe if the American innovation in the electric stack consistently came through partnerships with other countries, then the future of American innovation in the electric stack will consistently come through partnerships with other countries. Who knows? Maybe. Yeah. Anyway, so you have to read lesson number 6 in an English accent, please, Jeremy.
What looks smart in the short term is actually dumb in the long term.
What looks well? Yeah, that's the dilemma, isn't it? The paradox. Yeah, in order to perhaps be the next great thing, you have to think outside the box, think differently to the norm, break the model.
Or just don't do what GM did and let loose of the technology they had, just because shit was hitting the fan, and you know, don't sell your semiconductor business when it's on the rise. When it's on the rise. All right, the last two. Let's kind of get here. So China has a specific playbook. We've heard about this. I think Packy's written about this for a while. It's really China's bet is kind of this ability to take ideas into action and do it really, really well. They actually, it's what's funny going back to this. They actually sucked at building like regular cars, like according to what he was saying. The car, a combustion engine, 300 or 30,000 parts. China struggled with that and wasn't very successful, but this integration of the electric stack, I don't think anyone does it better, and they're continuing to refine and improve, and that's their bet. That's their playbook. Ideas into action, coordinated effort, vertical integration. Um,
I think there's
and
one important factor to add there, one little footnote quote. And while China's manufacturing innovation is impressive, looking back at the story of each layer of the electric stack, it's hard to miss this fact. None of the initial breakthroughs were made in China. So, will that change in the future? Will the breakthroughs with this domination, will breakthroughs come from China? Which again, maybe that's why Nvidia are suddenly allowed to sell their chips in China to keep that. Lesson number 8: integration drives innovation. This is true at the company level and at the national level and at the personal level and the romantic level and the emotional level, perhaps too.
so, can the U.S. catch up to the electric stack, the electric slide? I don't know.
I would give it a 20% chance of success.
Yeah, they're betting on having the smartest models. China's saying, "Hey, we just want models that work, and we'll feed what comes through those models into our machine of taking ideas into scale, into action, into pieces and parts that the world wants to buy." Um, yeah, that was a tough last little piece. There's a lot of tech in this. It was definitely a challenging selection from a breakdown perspective. I'm glad I did it. I learned a bunch.
Yeah,
Um,
I learned a lot from this, and I'd recommend anybody who's remotely interested in technology to read the essay "The Electric Slide" by Packy McCormick on Not Boring. I it's so dense. It's just so densely packed with new knowledge, and helps us at Thinking on Paper connect the dots. Like we said, we speak about data centers in space, we speak about humanoids, we speak about artificial intelligence, we speak about blockchain and quantum computers, and all of those technologies are reliant to some degree on the electric stack, on the 4 layers of the electric stack that we've learned about here. So it's just more fuel, more nodes for the Thinking on Paper grand design of holistic technology.
so a couple ways you can stay in touch, guys. Thinking on paper.xyz. Instagram is actually getting some action right now. So at Thinking on Paper podcast, I think
Yep.
is on Instagram, and we're also on Substack. We have a dispatch called "What Are We Thinking," where we actually are attempting a grand research project. This research project is going to map emerging technologies across human impact areas like governance, like access, like equality, like um, all of that stuff. So stay tuned. We're trying new experiments. Hopefully, they're resonating. Thanks for hanging with us. Got a bunch of great guests coming up this next year. We were in space with data centers before anybody else.
We were. Be disruptive, stay curious,
Keep thinking on paper and learning in public.
and we'll see you next week.